Ever feel like you're just scratching the surface when it comes to understanding computers? Like you get the basics, but deep down, you're curious about the real magic happening under the hood.
It's that itch to grasp the essence of computation, right? To see the invisible gears turning, to get that satisfying aha moment when it all clicks.
Exactly. And today, we're diving deep, way past the surface level. We're going to explore the fundamental theories, the core principles that make computers tick, and do it in a way that makes sense without getting lost in the jargon.
So we're not just going to tell you computers work because of algorithms. We're going to uncover what algorithms are at their heart, how they relate to the theoretical limits of what computers can do, and why understanding those limits is key to writing truly elegant and efficient code.
Our mission, should we choose to accept it, is to equip you with a powerful, intuitive grasp of these foundational concepts. Think of it as a mental toolbox for navigating the increasingly complex world of technology.
And our sources for this deep dive. Well, we've got some heavy hitters in the field of computer science. We'll be drawing from seminal texts like Sitzer's Introduction to the Theory of Computation and Corman, Laserson, Rivest, and Stein's Introduction to Algorithms, affectionately known as CLRS.
So buckle up because we're about to embark on a thrilling journey through the theoretical and practical landscapes of computation. First stop, the theoretical boundaries of what computers can even do. We're starting with something called finite automata. Have you ever encountered these curious little machines?
Oh, they're more common than you might think. Imagine a device with a very limited memory, almost like a light switch that can only be on or off. You can receive input, but it can only remember a finite number of things about that input.
A light switch with memory. Okay, I'm intrigued. How would this even begin to represent a computation?
Think about it this way. A finite automaton has a fixed set of states it can be in, kind of like those on or off positions for our light switch, but maybe with a few more options. It also has an alphabet of symbols it understands as input.
So it's like feeding it a sequence of these symbols, like a string of characters.
Right, and based on the current state it's in and the symbol it receives, it transitions to a new state. This change is governed by a set of rules, a kind of transition function that says, if you're in state A and you see symbol X, move to state B.
So it's bouncing between these states based on the input it's getting. But how does this tell us if the input is accepted or not?
Ah, that's where the accepting states come in. If, after processing the entire input string, the automaton ends up in one of its designated accepting states, then we say it accepts the string. It's like reaching a specific destination on a map after following a set of directions.
Okay, I can see how this could be used to recognize some simple patterns, but what are the limitations? Like, what kinds of things can finite automata not do?
Their biggest limitation is right there in the name, finite memory. They can only remember a fixed amount of information, regardless of how long the input is. So if you need to keep track of an unbounded amount of data, you're out of luck.
Can you give us some concrete examples of what they can recognize? Our sources have some interesting ones.
Absolutely. Let's say we have an alphabet of just 0 and 1. A finite automaton can easily recognize strings with exactly one 1 in them. It could start in a haven't seen a 1 state, then transition to a saw a 1 state if it encounters a 1. Any additional ones would send it to a too many 1 state, which wouldn't be an accepting state.
So it's using its limited memory to essentially count up to 1. What about recognizing strings with at least one 1?
Also very doable. You just need 2 states, haven't seen a 1 and have seen a 1. Once you transition to have seen a 1, you stay there, and that becomes your accepting state. The memory only needs to track if it's encountered a 1 or not.
What about something more complex, like strings containing a specific sequence, like 001?
Still within their capabilities. You would need more states to represent the different stages of seeing that sequence. A start state, a saw a 0 state, a saw 20 state, and finally an accepting saw 001 state. Any deviation from the sequence would reset the automaton to an earlier state.
So it's like a little pattern matching machine. What if you wanted to ensure every 0 is followed by at least 101?
You could do that by having states that, remember, if the last symbol seen was a 0, if it was, the next input must be a 1 to avoid reaching a non-accepting state.
Okay, I'm starting to get a feel for the kinds of patterns they excel at. What about things like even-length strings, or strings whose length is a multiple of 3?
For those, you'd use a small number of states, say 2 for even length and 3 for multiples of 3. The automaton cycles through these states with each input symbol, accepting only if it ends up in the correct state based on the length.
It's like using the states to keep track of a counter or a remainder. What if you wanted to recognize very specific strings, like 01 or 10?
In those cases, you could essentially create separate paths within the automaton, each leading to an accepting state. The paths would correspond to the exact sequences you want to recognize.
So finite automata are good at recognizing simple patterns, repeating sequences, and keeping track of basic counts. But what about more complex languages, ones with potentially nested structures? Our sources briefly mentioned context-free grammars, CFGs, and push-down automata, PDAs. Did those come into play here?
Absolutely. CFGs and PDAs represent the next level of computational power. The key difference is that they introduce a stack, which acts as a kind of unlimited notepad alongside the finite state machine.
A stack, like a pile of papers where you can only add or remove from the top?
Precisely. A push-down automaton can do everything a finite automaton can, but it can also push symbols onto the stack and pop them off. This stack gives them the ability to remember more context about the input they've seen.
So they can handle languages that require keeping track of more than just a finite amount of information?
Exactly. Imagine the language of palindromes, strings that read the same forward and backward like race car, or the language of strings with an equal number of zeros and ones, like 0011 or VM10. A PDA can use its stack to count the number of zeros it sees and then match them with ones, accepting only if the stack is empty at the end.
That makes sense. A finite automaton wouldn't be able to keep track of an arbitrary count like that. So PDAs and CFGs are essential for handling more intricate, nested structures like those found in programming languages, right?
Exactly. Think about parsing a mathematical expression with nested parentheses. A PDA with its stack can easily keep track of the opening and closing parentheses to ensure they're balanced.
Okay, so we've got finite automata for basic patterns and PDAs for more complex languages. But what about the big kahuna, the model that really captures the essence of what computers can do? That would be the Turing machine, right?
Ah, yes, the legendary Turing machine. This theoretical model takes computation to a whole new level. And instead of a finite number of states or a single stack, a Turing machine has a potentially infinite memory in the form of a tape.
An infinite tape. That sounds more like a philosophical concept than a practical one.
It is abstract, but it's a beautifully simple yet powerful idea. Imagine an infinitely long strip of paper divided into cells. The Turing machine has a read-write head that can move along this tape, reading and writing symbols.
So how does it work? You feed it some input, and then what?
The input is initially written on the tape, and the head starts at the beginning of the input. The machine has a set of states and a transition function that dictates its actions based on its current state and the symbol it reads from the tape.
So it's like a finite automaton, but with this infinite tape to work with.
In a way, yes, but the crucial difference is that the Turing machine can not only read the tape, but also write to it, changing the symbols. And it can move its head both left and right along the tape.
So it can actually manipulate its memory, not just read it. What determines when the computation stops?
The Turing machine has specific accept and reject states. When it enters one of these states, it halts. If it halts in an accept state, we say it accepts the input. If it halts in a reject state, it rejects the input. It might also run forever without halting.
It's like a program that either terminates with the result or gets stuck in an infinite loop.
A very apt analogy. And here's the profound part. The Church-Turing thesis, a cornerstone of computer science, essentially states that anything that can be computed algorithmically can be computed by a Turing machine.
So the Turing machine represents the ultimate limit of what computers can do.
That's the idea. It defines the theoretical boundaries of computation. Now, this brings us to the fascinating concepts of decidability and undecidability.
Decidability of whether a problem can even be solved by a computer, no matter how powerful.
Precisely. A problem is decidable if there exists a Turing machine that will always halt and give a correct yes or no answer for any input. If no such Turing machine exists, the problem is undecidable.
So decidable problems are those for which we can always write a program that will give us a definite answer. Can you give an example of a decidable problem related to the languages we've discussed?
Sure, the problem of determining whether a given context-free grammar can generate a specific string is decidable. You could systematically explore all possible derivations in the grammar up to a certain length and check if the string can be produced.
Okay, what about undecidable problems? Those sound a bit more mind-bending.
Here's where things get really interesting. The problem of determining whether the language recognized by an arbitrary Turing machine is regular, context-free, or even decidable is itself undecidable.
So there's no universal algorithm that can analyze any Turing machine and tell us these fundamental things about it. That's a pretty profound limitation.
It is.
Hmm.
It highlights the inherent limits to our ability to fully understand and analyze the behavior of arbitrary computer programs. Rice's theorem, a general result in this area, states that any non-trivial property about the languages recognized by Turing machines is undecidable.
That's wild. It means there are things about computer programs that we can never know for sure, no matter how clever our algorithms are.
Exactly. It's a humbling reminder of the vastness and complexity of the computational universe. To explore these limits further, we can introduce the concept of Oracle Turing machines.
An oracle. Sounds mystical.
It's a kind of thought experiment. Imagine a Turing machine that has access to an oracle that can instantly answer specific questions, even if those questions are normally undecidable. It's like having a magic 8-ball that always gives the right answer, even for incredibly difficult problems.
So it's a way to explore what becomes possible if we had this hypothetical, all-knowing entity to help us.
Exactly. It allows us to study the relative difficulty of computational problems and understand how much power a particular oracle would give us. Okay, we've spent a good amount of time in the theoretical realm. Now let's shift gears and talk about the more practical side of computation. How we actually design algorithms to solve problems efficiently.
Algorithms, the recipes that drive our software, the step-by-step procedures that computers follow. But it's not just about getting an answer, it's about getting it fast, especially when we're dealing with massive amounts of data.
Absolutely. Efficiency is key. And when we talk about the efficiency of an algorithm, we're primarily concerned with its running time, how the number of steps it takes scales with the size of the input.
So how do we measure and compare the running time of algorithms in a way that's independent of the specific hardware or programming language?
That's where asymptotic notation comes in, specifically big O notation. Big O notation gives us a way to describe the growth rate of an algorithm's running time as the input size gets very large. It focuses on the dominant terms and ignores constant factors and lower order terms.
So it's like saying, for large enough inputs, this algorithm will generally behave like this.
Right. For example, an algorithm with a running time of O and log will be significantly faster for large inputs than an algorithm with a running time of O and 2, even if the O and 2 algorithm might be slightly better for very small inflows.
Can you give us some classic examples of algorithms with different running times?
Sure, merge sort, which has a running time of O(n) log n, is generally more efficient than insertion sort, which has a running time of O and 2.
Okay, so understanding big O notation helps us compare algorithms and choose the best ones for our needs. Now, let's talk about strategies for designing efficient algorithms. One that often comes up is divide and conquer.
Yes, a very elegant and powerful paradigm. The core idea is to break down a problem into smaller subproblems of the same type, solve those recursively, and then combine the solutions to get the answer for the original problem.
Like with merge sort, you keep dividing the array in half until you have single element arrays, which are already sorted, and then you merge them back together in a sorted way.
Exactly. And this recursive structure leads to a specific kind of equation called a recurrence relation, which we can use to analyze the running time of divide and conquer algorithms.
So by solving the recurrence, we can figure out the big O running time of the whole algorithm.
Precisely. There are techniques for solving these recurrences, and there's even a handy tool called the master method that gives us a quick way to determine the solution for many common cases.
Divide and conquer is a clever approach. It's like breaking down a complex task into smaller, more manageable pieces. Now, let's move on to another area that plays a huge role in algorithm design, graph theory.
Graphs are incredibly versatile structures. They allow us to model relationships between entities, which can be anything from people in a social network to cities on a map or even web pages on the internet.
I remember when I first learned about graphs, I thought they were just diagrams with circles and lines, but there's so much more than that, right?
Absolutely. The circles are called vertices, and the lines are called edges. Edges can be directed, representing a one-way relationship, or undirected, representing a mutual relationship.
And how do we represent these graphs in a computer's memory so we can work with them algorithmically?
There are two common ways: adjacency lists and adjacency matrices. Adjacency lists are efficient for sparse graphs, where the number of edges is relatively small. Adjacency matrices are better for dense graphs, or when we need to quickly check if an edge exists between two vertices.
So once we have a graph representation, what kind of problems can we solve using graph algorithms?
Oh, there's a whole treasure trove of algorithms for working with graphs. Breadth first search, BFS, is a classic one for exploring a graph level by level. like finding all your friends on a social network, then their friends, and so on. It's great for finding shortest paths in unweighted graphs.
What about depth-first search, DFS? That sounds like a different way of traversing a graph.
Yes, DFS explores as far as possible along each branch before backtracking. It's useful for tasks like detecting cycles in a graph or finding strongly connected components, groups of vertices where you can get from any vertex to any other within the group.
What about graphs where the edges have weights, like distances on a map?
For those, we have algorithms like Dijkstra's algorithm for finding shortest paths in weighted graphs with non-negative edge weights. And if we need to handle negative edge weights, there's the Bellman-Ford algorithm.
What about the problem of finding the minimum spanning tree of a graph? That's like finding the cheapest way to connect all the vertices using the edges.
Yes, and we have efficient algorithms for that too, like Kruskal's algorithm and Prim's algorithm. These are greedy algorithms that make locally optimal choices at each step to find the globally optimal solution.
It's amazing how many problems can be modeled and solved using graphs. Now let's wrap up our discussion of algorithms with one of the biggest unsolved mysteries in computer science, the P versus NP problem.
Ah, yes, a problem that has captivated mathematicians and computer scientists for decades. It boils down to the question of whether every problem whose solution can be efficiently verified can also be efficiently solved.
Efficiently, meaning solvable in polynomial time, right?
Exactly. The complexity class P represents the set of problems that can be solved in polynomial time. NP, on the other hand, stands for non-deterministic polynomial time. It includes problems where a proposed solution can be verified in polynomial time.
So for a problem in NP, it might be really hard to find a solution, but if someone gives you one, you can quickly check if it's correct.
Precisely. Many important problems are in NP, like the traveling salesperson problem, where you want to find the shortest route that visits a set of cities exactly once, or the Boolean satisfiability problem, SAT, where you need to determine if there's a way to assign truth values to variables to make a logical formula true.
And the big question is P equal to NP? If it is, then finding solutions to these hard problems would be just as easy as checking them.
That's right. If equals NP, it would have huge implications for fields like cryptography, optimization, and artificial intelligence. But most computer scientists believe P is not equal to NP, meaning there are problems in NP that are inherently harder to solve than to verify.
So we're likely stuck with these difficult problems.
Well, not necessarily. Even if P doesn't equal NP, there are still approaches we can take. We can develop approximation algorithms that find near-optimal solutions, or we can focus on special cases of the problems that are easier to solve.
The source also mentions NP-complete problems. What are those?
NP-complete problems are the hardest problems at NP. They have the property that if you could solve any one of them in polynomial time, you could solve all of them in polynomial time, and P would equal NP.
So they're like the key to unlocking the whole mystery of P versus NP.
Exactly. SAT, the Boolean satisfiability problem, is a classic example of an NP-complete problem. If you could find a truly efficient algorithm for SAT, you would have cracked the P versus NP problem.
That's a lot to ponder. This whole discussion of P versus NP really highlights the boundaries of what we can compute efficiently. Now let's step back and think about how these theoretical concepts relate to the real world of computing.
Even though they might seem abstract, these ideas have a profound impact on the technology we use every day.
Like, how do finite automata show up in real life?
They're used in text searching, compilers, and network protocols. They're the workhorses behind pattern matching, breaking down code into tokens, and managing network connections.
And what about Turing machines? We don't actually build those, do we?
No, but the Turing machine is the theoretical foundation for the very concept of a general-purpose computer. It defined the ultimate limits of what any computer program can do.
And the efficiency of algorithms, the big O notation, how does that matter in practice?
It determines how well our software performs. Inefficient algorithms would make many of the applications we use daily, like search engines and social networks, unbearably slow.
What about graph algorithms? Where do we see those in action?
Oh, everywhere. Social networks, mapping apps, network infrastructure, recommendation systems, they all rely heavily on graph algorithms to analyze relationships, find shortest paths, and optimize connections.
And the P versus NP question, even though it's unsolved, does it have practical consequences?
Absolutely. It guides the development of cryptographic systems and influences how we approach hard problems in fields like operations research and artificial intelligence. It helps us set realistic expectations about what we can compute efficiently.
It's amazing how these theoretical foundations of computing underpin so much of our digital world. It's like understanding the invisible forces that shape our reality.
It's about seeing the deeper connections between abstract ideas and the technology that permeates our lives. It's about appreciating the power and the limitations of computation.
This has been a fantastic deep dive. We've covered a lot of ground, from simple models of computation to the complexities of algorithms and the profound implications of the P versus NP problem.
And hopefully we've equipped you with a new lens through which to view the digital world, one that reveals the intricate mechanisms beneath the surface.
So, as we conclude, here's a final thought for you to ponder. What emerging frontiers in computing do you find most exciting? Or how might a deeper understanding of these foundational concepts influence your own relationship with technology? The journey of exploration doesn't end here. There's a whole universe of knowledge out there waiting to be discovered. Thanks for joining us on this deep dive.
And remember, the beauty of computation lies not just in its practical applications, but also in the elegant theories and the profound questions that continue to drive our understanding of this fascinating field.
Until next time, keep exploring, keep questioning, and keep pushing the boundaries of what's possible.
Happy computing!
Happy computing.